Hello friends, in this podcast we are going to learn p block elements. It is very important chapter for class 11th chemistry students. Elements in which valence electrons enters in the p orbital are known as p block elements. The only exceptional element in this block is helium, atomic number 2, that has the electronic configuration 1s2. The general valence shell electronic configuration of p block elements is ns2np126. They are placed to the right hand side of long form of periodic table and includes elements belonging to group 13 to 18. They consist of metals, metalloids, non-metals and noble gases. There are 6 families in the p block elements, that is group 13. Name of family is boron family. Outermost electronic configuration is ns2np1 and name of elements is boron, aluminium, gallium, indium, thallium. Next is group 14. Name of family is carbon family. Outermost electronic configuration is ns2np2 and name of elements is carbon, silicon, germanium, tin, lead. Next is group 15 elements or group 15 family. Name of family is nitrogen family. Outermost electronic configuration of nitrogen family is ns2np3 and name of elements is nitrogen, phosphorus, arsenic, antimony, bismuth. Next is group 16. Name of family is chalcogens, that is oxygen families. Outermost electronic configuration is ns2np4. Name of elements of oxygen family is oxygen, sulfur, selenium, tellurium, polonium. Next is group 17. Name of family is halogens, that is fluorine family. Outermost electronic configuration is ns2np5. Name of elements of fluorine family is fluorine, chlorine, bromine, iodine, astatine. Next is group 18. Name of family is noble gases. Outermost electronic configuration is ns2np6 and name of elements of group 18 elements is helium, neon, argon, krypton, xenon, radon. Now we are going to discuss about group 13 elements, that is boron family. Group 13 elements contain 5 elements, namely boron, aluminium, gallium, indium and thallium. Symbol for boron is B, symbol for aluminium is Al, symbol of gallium is Ga, symbol of indium is In, symbol of thallium is Tl. The outermost electronic configuration of group 13 elements is ns2np1. Boron is a semi-metal while aluminium and rest of the elements are metallic in nature. Semi-metals are also known as metalloids. Occurrence: boron does not occur in free state in the nature. It is fairly rare element. It mainly occurs as borates, orthoboric acid, borax and kernite. It shows two isotopic forms as 10B in 19% and 11B in 81%. Aluminium also does not occur in free state. It is fourth most abundant element in the earth crust. I repeat, aluminium is the fourth most abundant element in the earth crust. Important minerals of aluminium are bauxite and cryolite. Gallium, indium, thallium are less abundant elements in nature. Thallium is highly toxic among the group. Physical properties. Atomic radii. On moving down the group, atomic radii increases due to increase in extra shell of electrons, but atomic radius of gallium is less than that of aluminium. This is because of variation in the inner core of the electronic configuration. Ionization enthalpy. On moving down the group, regular decrease trend accepted in the ionization enthalpy values is not observed. It decreases from boron to aluminium and increases in gallium, and again decreases in indium, then increases in tellurium. Electropositive or metallic character. The elements of group 13 are less electropositive than S block elements. The electropositive character increases from boron to aluminium and then decreases from aluminium to tellurium. Aluminium is metal and is most electropositive. Lewis acids. Trivalent compound of group 13 such as BCl3, BF3, AlCl3 etc. have 6 electrons around the central atom and thus act as Lewis acids by accepting a lone pair of electrons to achieve stable electronic configuration. Lewis acids character decreases down the group. Oxidation states. Boron shows only +3 oxidation state, while other elements shows +1 oxidation state as well as +3 oxidation state. Chemical reactivity. Action of air. Oxygen. Action of air or oxygen. Boron is unreactive towards air in crystalline form, while amorphous boron and aluminium metal on heating in air forms B2O3 and Al2O3. Also with nitrogen at high temperature they form nitrides. All the members of this group forms oxides of the type E2O3. 4E plus 3O on heating gives 2E2O3 and 2E plus N2 gives 2En, where E is equal to B, Al, Ga, In and Tl. Oxidation of B is acid. Oxides of B is acidic. Al and Ga oxides are amphoteric and those of In and Tl are basic in their properties. Reactivity towards water. Pure boron does not react with water, while it reacts with steam at red heat. Aluminium decomposes boiling water, evolving hydrogen. Gallium and indium are not attacked by water. 2Al plus 3H2O gives Al2O3 plus 3H2, that is hydrogen gas. Reactivity towards halogens. All the elements of group 13 reacts with halogens to form trihalides except TlI3. 2E plus 3x2 gives 2ex3, where x is equal to FClBrI and E is equal to BAlGaInTl. Reactivity towards acids. Boron does not react with non-oxidizing acids like HCl and dilute H2SO4, but with oxidizing acid like concentrated H2SO4 and HNO3, boron forms boric acid. So B plus 3HNO3 gives H3BO3 plus 3NO2 and 2B plus 3H2SO4 gives 2H3BO3 plus 3SO2. While other elements react with any acid to form trivalent salt, that is 2E plus 6HCl gives 2ECl plus 3H2 and 2E plus 3H2SO4 gives E2SO43 plus 3H2. Reactivity towards alkalis. Boron and aluminium react with alkalis to give borates and meta-aluminate with the evolution of H2 gas. So 2B plus 6NaOH in presence of fuse gives 2Na3BO3 plus 3H2. 2Al plus 2NaOH plus 2H2O gives 2NaAlO2 plus 3H2. Indium and thallium are not affected by alkalis. Reducing action of boron. Boron is powerful reducing agent and it reduces CO2, SiO2 to C and Si respectively. That is 4B plus 3CO2 gives 2B2O3 plus 3C and 4B plus 3SiO2 gives 2B2O3 plus 3Si. Anomalous properties of first element boron. Boron differs from other member of group 13 because of its small size, that is 88 picometer, higher electronegativity, that is 2.0, and higher value of ionization enthalpy, that is 801 kilojoule per mole. It shows following different properties. Boron is a non-metal while other members are metals. Boron shows allotropy while other members do not. Boron has highest melting and boiling point among the elements of group 13. Oxides and hydroxides of boron are weakly acidic or of aluminium are amphoteric while those of rest of the members are weakly basic. Boron hydride is quite stable while hydrides of other elements are less stable. Important compounds of boron. First is borax. It is also known as sodium tetraborate, decahydrate, Na2B4O7.10H2O. Borax occurs naturally as tincal. It is obtained from the mineral colemanite by boiling it with a solution of Na2CO3. So Ca2B6O11 plus 2Na2CO3 gives Na2B4O7 plus 2NaBO2 plus 2CaCO3. Properties. Aqueous solution of boron is alkaline due to hydrolysis. So Na2B4O7 plus 7H2O gives 2NaOH plus 4H3BO3. Boron when heated with ethyl alcohol and concentrated H2SO4, it gives volatile vapors of triethyl borate which burn with green edge flame. It is used as test for borate radical in quantitative analysis. Borax bead is used to detect colored radicals. It is transparent glassy mass. Orthoboric acid H3BO3. Orthoboric acid is a white crystalline solid with a soapy touch. It is obtained from borax by treating with dilute HCl and dilute H2SO4. Na2B4O7 plus 2HCl plus 5H2O gives NaCl plus 4H3BO3. It can also be obtained from mineral colemanite by passing SO2 through mixture of powdered mineral and boiling water. So Ca2B6O11 plus 4SO2 plus 11H2O gives 2CaHSO3 2 plus 6H3BO3. Properties: it is a weak monobasic acid and behaves as a Lewis acid. It accepts pair of electron from OH minus ion of H2O. H3BO3 plus H2O gives BOH4 minus plus H plus. On heating it at 370 Kelvin, it forms metaboric acid HBO2, which on further heating gives boric oxide B2O3. So H3BO3 on heating gives HBO2, which on further heating gives B2O3. With NaOH, it forms sodium metaborate. H3BO3 plus 4 NaOH gives NaBO2 plus 2H2O. With ethyl alcohol and concentrated H2SO4, it gives triethyl borate, which burns with green edged flame. That is H3BO3 plus 3C2H5OH in presence of concentrated H2SO4 gives BOC2H5 thrice plus 3H2O. Dear student, if you not understand reactions which I explain, please visit our website www.chemistrynotesinfo.com. In 11th section you find chapter P block elements. Please open that chapter and read that chapter so you can understand reactions very clearly. Alternatively, you can join our channel or you can join our Telegram channel to download notes of this chapter. Next compound is diboron B2H6. It is the simplest boron hydride. It is prepared by treating boron trifluoride with LiAlH4 in ethyl ether. 4BF3 plus 3LiAlAH4 gives 2B2H6 plus 3LiF plus 3AlF3. I repeat, 4BF3 plus 3LiAlH4 gives 2B2H6 plus 3LiF plus 3AlF3. In laboratory, the boron is prepared by the oxidation of sodium borohydride with iodine. So 2NaBH4 plus I2 gives B2H6 plus 3NaI plus H2. In industry, it is prepared by the reaction of BF3 with NaH. So 2BF3 plus 6NaH gives B2H6 plus 6NaF. Properties: boron is colorless, highly toxic gas. Diboron is colorless, highly toxic gas. It has boiling point of 180 Kelvin. It catches fire spontaneously. When it is exposed to atmospheric air, it burns in oxygen. The reaction is highly exothermic. B2H6 plus 3O2 gives B2O3 plus 3H2O. is readily hydrolyzed by water to form boric acid. B2H6 plus 6H2O gives 2H3BO3 plus 6H2. With less bases, diboron first undergoes cleavage to form boron BH3, which then reacts to form adducts, that is B2H6 plus 2NMe3 gives 2BH3 plus NMe3. B2H6 plus 2CO gives 2BH3.CN. It reacts with strong alkalis to form metaborates. B2H6 plus 2KOH plus 2H2O gives 2KBO2 plus 6H2. I repeat, B2H6 plus 2KOH plus 2H2O gives 2KBO2 plus 6H2. When diboron reacts with LiH in presence of ether, it forms lithium borohydride, that is 2LiH plus B2H6 in presence of ether gives 2LiBH4. Now we are going to discuss group 14 elements, that is carbon family. The outermost electronic configuration of group 14 elements is NH2NP2. This group includes carbon, silicon, germanium, tin and lead. Symbol of carbon is C, symbol of silicon is Si, symbol of germanium is Ge, symbol of tin is Sn and symbol of lead is Pb. In our further discussion, I name these elements with their symbol. So please remember the symbol of these elements. I repeat again, symbol of carbon is C, symbol of silicon is Si, symbol of germanium is Ge, symbol of tin is Sn and symbol of lead is Pb. Carbon and silicon are non-metals. Germanium is a metalloid where tin and lead are metals. Occurrence: carbon is widely distributed in nature in free state as well as in the combined form. In elemental form, it occurs as coal, graphite, diamond, and in the combined form, it occurs as metal carbonates, hydrocarbons, and carbon dioxide. Silicon is the second most abundant element in the earth crust. By mass, it is about 27.7%. It is present in nature as silicon, SiO2, and silicates. Germanium exists only in traces. Tin occurs as SnO2 and lead as galena, PbS. Physical properties. Atomic radii. Atomic radii of group 14 elements regularly increases down the group. There is large increase in atomic radii from carbon to silicon, but from silicon inward there is a small increase due to ineffective shielding of the valence electrons by intervening d and f electrons. Ionization enthalpy. In general, ionization enthalpy decreases down the group. From carbon to silicon, there is large decrease in ionization enthalpy, but from tin to lead, there is slight increase. Electronegativity. Group 14 are slightly more electronegative than corresponding group 13 elements. Carbon is most electronegative element in this group. Electronegativity values from Si to Pb are almost same. Oxidation states. Carbon shows only +4 oxidation state, while other elements of the group shows +2 as well as +4 oxidation states. Chemical reactivity. Reactivity towards oxygen. All the elements of group 14 when heated in oxygen forms monoxides or dioxides, that is 2M plus O2 gives 2MO, M plus O2 give MO2, where M is equal to C, Si, Ge, Sn, Pb. C is carbon, Si is silicon, Ge is germanium, Sn tin, Pb lead. The dioxides of carbon, silicon and germanium are acidic in nature, and that of tin and lead are amphoteric in nature. The monoxides of carbon is neutral, germanium is distinctly acidic, while tin and lead are amphoteric. Reactivity towards water. Carbon, silicon, germanium are not affected by water but react on red heating to form oxides. Lead is unaffected by water. Tin decomposes steam to form dioxide and hydrogen gas. So, Sn plus 2H2O on heating give SnO2 plus 2H2. Reactivity towards halogens. Carbon forms only tetrahalides, while other elements of group react directly with halogens to form dihalides MX2 as well as tetrahalides. M plus X2 give MX2 except carbon. M plus 2X2 give MX4. Stability of dihalides increases down the group, while that of tetrahalides decreases down the group. Reactivity towards alkalis. Carbon is unaffected by alkalis, while Si, Sn and Pb are slowly attacked by cold alkalis to form silicate, stannates and plumbates respectively. M plus 2NaOH plus H2O gives Na2MO3 plus 2H2, where M is equal to Si, Sn, Pb. Anomalous properties of carbon. Carbon differs from rest of the elements of group 14 due to its smaller size, higher electronegativity and high ionization enthalpy. Some points of difference are: it is the hardest element of the group 14, it has the highest ionization enthalpy and is most electronegative element of this group. It has maximum covalency is for as d block elements, electrons are absent in the valence shell. Carbon has maximum covalency is 4 as d electrons are absent in the valence shell. It has maximum property of catenation. It can form multiple bonds. As result, carbon forms large number of compounds. Carbon dioxide CO2 is a gas, while the oxides of other elements are solids. Catenation. The property of self-linking of atoms of an element to form straight or unbranched chain and rings of different sizes by covalent bond is called catenation. I repeat, the property of self-linking of atoms of an element to form straight or unbranched chain and rings of different sizes by covalent bond is called catenation. The tendency of an element to form a chain depends upon the strength of the element bond. The tendency of an element to form a chain depends upon the strength of the element-element bond. Among the group 14 elements, carbon-carbon bond strength is 348 kilojoule per mole is maximum. Therefore, carbon shows maximum tendency of catenation. The order of catenation is carbon much larger than silicon, then germanium and tin. Lead does not show any type of catenation. Allotrophs of carbon. Allotropy is the phenomenon in which an element exists in different physical forms having different physical properties, but chemical properties are same or similar. I repeat, allotropy is the phenomena in which an element exists in different physical forms having different physical properties, but chemical properties are same. Among the elements of group 14, carbon, silicon and tin have allotropic modifications. Carbon has the largest number of allotropic modifications. Allotrophs of carbon. Carbon's crystalline allotrophs are diamond and graphite, and amorphous are charcoal and lamb black, and charcoal is from wood charcoal and animal charcoal. Dear friends, you are listening this podcast from www.chemistrynotesinfo.com. Now we are going to discuss allotrophs of carbon. First is diamond. Diamond has three-dimensional structure. Each carbon atom is bonded to four other carbon atoms which occupy four corners of a tetrahedron, and each of these to four more carbon atoms. In diamond, carbon atom is sp3 hybridized. Carbon-carbon bond length is 154 picometer. Diamond has high melting point of about 3873 Kelvin and high density of about 3.51 gram per centimeter. It is non-conductor of electricity, and it is non-conductor of electricity and hardest on the earth. Graphite. Graphite has two-dimensional sheet-like structure. These are fused system of planar hexagonal ring. In the planar hexagonal ring, each carbon atom is bonded to three other carbon atoms. In graphite, carbon atoms undergoes sp2 hybridization. In graphite, the distance between two successive layers is 340 picometer, while bond length is 141.5 picometer. It conducts electricity. Now we are going to discuss about fluorines or buckyballs. Fluorines is newly discovered allotrope of carbon, which is discovered in 1985. Fluorines are made by heating of graphite in an electric arc in presence of inert gases such as helium or argon. It is cage-like structure molecule with chemical formula C60. It has a shape like saucer ball or called as Buckminster fluorines. Each carbon atom is sp2 hybridized. The average carbon-carbon distance is 144 picometer. Important compounds of carbon or oxides of carbon. Carbon monoxide CO. It is prepared by direct combination of carbon in limited supply of oxygen. 2C plus O2 gives 2CO. By laboratory method, pure CO is prepared by dehydration of formic acid with concentrated H2SO4 at 373 Kelvin. HCOOH in presence of H2SO4 at 373 Kelvin gives CO plus H2O. On commercial scale, it is prepared by the passage of steam over hot coke. So, C plus H2O gives CO plus H2. When air is used instead of steam, a mixture of CO and N2 is produced, which is called producer gas. 2C plus O2 plus 4N2 at 1273 Kelvin gives 2CO plus 4N2. Properties. It is colorless and odorless gas and almost insoluble in water. It is powerful reducing in water. It is powerful reducing agent and reduces almost all the metal oxides. CO is used in the extraction of many metals from their oxides. Fe2O3 plus 3CO on heating gives 2Fe plus 3CO2. CuO plus CO on heating gives Cu plus CO2. ZnO plus CO gives Zn plus CO2. It is a poisonous gas and burns with blue flame, and when inhaled produces suffocation and finally death. Carbon dioxide. It is prepared by complete combustion of carbon and carbon containing fossil fuels in excess of air. Carbon plus O2 on heating gives CO2. CH4 plus 2O2 on heating gives CO2 plus 2H2O. It is prepared in laboratory by the action of dilute HCl on CaCO3. So, CaCO3 plus 2HCl gives CaCl2 plus CO2 plus H2O. On commercial scale, it is obtained by heating limestone. CaCO3 in at 1600 Kelvin gives CaO plus 6 plus CO2. It is obtained as a byproduct of manufacturing of ethyl alcohol by fermentation of glucose or fructose. C6H12O6 in presence of zymase gives 2C2H5OH plus 2CO2. Properties. Carbon dioxide is colorless, odorless and tasteless gas. It is slightly soluble in water and is heavier than air. CO2 is acidic in nature. It combines with alkalis to form metal carbonates. CO2 acts as an oxidizing agent when heated with zinc, iron or carbon. These are oxidized. Zn plus CO2 gives ZnO plus CO. CO2 plus C gives 2CO. In photosynthesis, CO2 is converted to glucose and oxygen. 6 CO2 plus 12 H2O gives C6H12O6 plus 6 H2O plus 6 O2. CO2 reacts with NH3 at 453 Kelvin to 473 Kelvin under a pressure of 220 atmosphere to give urea as the final product. 2NH3 plus CO2 at 453 Kelvin to 473 Kelvin at 220 atm pressure gives NH2CO NH2 plus H2O. Compounds of silicon. Silicon dioxide SiO2. Silicon dioxide is commonly known as silica. 95% of earth crust is made up of silica and silicates. It occurs as quartz, cristabalite and tridymite, which are crystalline. SiO2 is covalent in nature and in normal form it is non-reactive because of very high SiO bond enthalpy. However, it is attacked by HF and NaOH. SiO2 plus 4HF gives SiF4 plus 2H2O. SiO2 plus 2NaOH gives Na2SiO3 plus H2O. Silicon tetrachloride SiCl4. It is prepared by action of chlorine on silicon. Si plus 2Cl2 gives SiCl4. This tetrahalide is covalent in nature and possesses tetrahedral geometry. CCl4 is not hydrolyzed by water, but SiCl4 gets easily hydrolyzed. SiCl4 plus 4H2O gives SiOH4 plus 4HCl. Silicones. Silicones are synthetic organosilicon compounds containing repeated R2SiO units held by SiO-Si linkage. These are formed by the hydrolysis of alkyl or aryl substituted chlorosilicnanes and their subsequent polymerization. Silicates. Silicates are metals derivatives of silicic acid, H4SiO4 or SiOH4. Silicates are formed by heating metal oxides or metal carbonates with sand. Example: Na2CO3 with fused with sand and SiO2 gives Na4SiO4. Silicates can also be termed as metallic salts of silicon, oxygen, and ions. Silicates have basic unit of SiO4 4 minus. Each silicon atom is bounded with 4 oxide ions tetrahedrally. Rocks, clays, soils are made up of silicates of aluminium, iron, magnesium, and other metals. Thank you to listening this podcast. This podcast is brought to you by www.chemistrynotesinfo.com. You can follow us at Instagram, Facebook, and Telegram. Also find us at YouTube. Thank you to listening this podcast.